My name is Nomla Lavan Reddy. I am from Institute of Aeronautical Engineering College. My roll number is 219518665. My branch is CSE ANML. I am from section A. I am here to present a TikTok video of LAG subject. I have selected a topic from LAG, that is, the topic name is Control of Non-Holonomic Systems and Decomposition of Skew Symmetric Matrices. This is my topic. Before going to the topic, let us know about what is skew symmetric matrix. Yes, introduction. Skew symmetric matrix. In mathematics, a skew symmetric matrix is defined as a square matrix that is equal to the negative of its transpose matrix. For any square matrix A, the transpose matrix is given as A transpose. A skew symmetric matrix or anti-symmetric matrix A can be represented as A is equal to minus A transpose. Here some terms are there. Let us know about that. What is square matrix? Square matrix means the order should be same, the row and column should be same. It is square matrix. The transpose means the columns are interchanged to rows and rows are changed to columns, that is transpose. If A is equal to minus A transpose, that is skew symmetric matrix. If A is equal to A transpose, that is symmetric matrix. In this topic we discuss about skew symmetric matrix, which is A is equal to minus A transpose. Let us see some example here. A is equal to 0 3 minus 2 minus 3 0 4 2 minus 4 0. It is a skew symmetric matrix by which A transpose is equal to minus A, which is A is equal to minus A transpose. This is about skew symmetric matrix. And here in topic we have non-holomonic systems. What is non-holomonic systems means? Let us know by example. The simple example of non-holomonic system can be a wheel that rolls on a plane surface, such as a unicycle. The contrast here arises due to the roll without a slip condition. The configuration in the generalized coordinate vector is q is equal to x comma y comma z. Next we discuss about let us discuss this to pick up with some examples or problems. We consider some applications of the following two problems to non-linear control and linear algebra. First problem is for a given skew symmetric matrix S with elements belonging to the commutative algebra to decompose first to see what is the given skew symmetric matrix. Let S is equal to sigma I equal to 1 to k xi symmetric of yi k comma k less than infinity. Here xi symmetric yi means xi yi transpose minus yi xi transpose. Of course it is derivable to minimize such k. Here symmetric symbol is we know in sets we discussed or we know that xi x or let's take a b. A symmetric B means A union B minus A intersection B, like that. Here in matrix S, xi symmetric yi means xi yi transpose minus yi xi transpose. Next, in problem B, let us know about optimal decomposition for a given skew symmetric matrix S is S with complex elements and positive numbers C1, C2 and so on Cn. To solve the following optimization problem, S is equal to sigma I equal to 1 to infinity xi symmetric yi sigma I equal to 1 to infinity. Here we take an xi mod of det square plus a yi det of mod square of ci, that is infinitum minimum. Here xi dot whole square y we taken is transpose and transpose of a matrix and matrix that is same. So if you that it is square become square. Next, before we consider the following application, let us know what problem B gives us. First, problem A, non-holonomic motion planning and feedback stabilization. This is the problem A discussed is gives the non-holonomic motion planning and feedback stabilization. In problem B, we get a non-variational approach to some non-linear optimal control problems and non-convex spectral inequalities. We have discussed in problem 2. This is about non-variational approach to some non-linear optimal control problems and non-convex spectral equalities. In 1 and 2, it has been shown how a decomposition of a skew symmetric matrix. Here look at that. S is equal to sigma I equal to 1 to infinity xi symmetric yi. Here S is equal to minus S transpose. We know that it is a definition of a skew symmetric matrix that we discussed earlier. Xi symmetric yi means xi yi transpose means yi xi transpose, which is discussed in problem 1. Now, where S belongs to Kn, 2 belongs to Kn, xi comma yi belongs to K per n. K is a commutative algebra over the field of real numbers, can be used for a feedback stabilization of globally controllable control system. X is equal to A of x u. Let's consider equation 1. Okay. Now, from the other hand, we will show in this paper how one may obtain new spectral inequalities for matrices using an optimal control problem of the following classical type. First, we take an x equal to A of x u in equation 1. In equation 2, we take x equal to x of u. X of 0 is x. X of 1 is, take z. Here, integration of 0 to 1 u comma u dt, we get a minimum value. Now, here the crucial point is in this reduction. In equation 2, the crucial point in this equation 2 is the time scalability property for 2. We would like to point out here that as the development of linear control theory 2 decades ago gave a push to the development of linear algebra. Here, 2 decades ago, development of the linear control give us linear algebra. Non-holonomic control theory will enrich polynomial algebra. Next, let us discuss about decomposition of skew symmetric matrices and stabilization of non-holonomic systems. Suppose that non-holonomic system x is equal to sigma I equal to 1 to m bi x ui equal to b of x u. Let us consider this as a equation 3. Next, let us discuss about problem 1. Dynamical system y is equal to f of y comma t and closed ball b is equal to b of x comma delta are given with f smooth enough. Find feedback loss ui is equal to ui of x comma t such that xi is equal to sigma bi of xi ui x comma I. Here x of 0 is equal to y of 0 and mod of xi minus yi c of 0 comma 25 tends to 0 uniformly on x of 0 belongs to b. Here remark 1 is usually nominal dynamical system in time is the usually nominal dynamical system is time invariant. Y is equal to f of phi. Now, motion planning for control system is given as follows. X of 0 is equal to x bar, x of 2 pi is equal to x bar of t. This not belongs to obstacle set. This not belongs to obstacle set. So what is needed from the nominal system is the following. If y of 0 is equal to x, then y of t not belongs to optical set, and it is similar to x of the 2 pi. Now, if once if one uses a feedback approach to this problem, then y of t belongs to x tends to 0. In 1, 2 problems, it was shown how a case of higher order Lie brackets can be easily recursively reduced to the case of first order lie brackets alone by using a finite set of different small parameters c1 to ck, k being the highest order of lie brackets in equation 1. This procedure is in some sense similar to a Eisenberg approach to pole assignment in linear control theory in equation 3 we discussed. Here we consider the case of first order lie brackets to illustrate the general idea of this paper. So suppose that c of x is equal to bi so on bm. Let us I is here 1 less than equal to I less than j less than or equal to m. Here bi comma bj is the partial differentiation delta bi by delta x bi minus delta by delta x bj. Next is we consider the following structure for a feedback solution. For feedback solution, we consider this following structure. This is a structure. Here in this structure, here skew of this one is a skew symmetric matrix, which are part of symmetric of I and j. Here I is less than j, and next is the following 3 steps produce the solution using feedback structure 4. By this step 1, step 2, step 3 are there. With these 3 steps we can get a feedback structure 4. First step is delta 1 bar, delta 2 bar, and so on delta n bar, where I less than or equal to up to delta ij, where I can j is in the range 1 less than or equal to I less than j less than or equal to m. Now C transpose F is equal to C transpose of C transpose whole power that is inverse 1 power minus 1 means that is inverse of C transpose F of x comma t. In step 2, decomposition of skew symmetric matrix, that is symmetric of that A of A bar of j ij, that is equal to sigma of I equal to 1 to m equal to 1 of alpha 1 symmetric of beta 1, that is alpha 1 symmetric of beta 1 means alpha 1 beta 1 transpose minus beta 1 alpha 1 transpose, where alpha 1 is a1 to 0 whole per transpose, beta 1 means 0 comma 0 comma that's so on is equal to 0 whole per transpose, where L and M belongs to 1 less than or equal to M less than or equal to M minus 1. Let us consider step 3, compute. By these all doing from these 3 steps we get is the obviously only step 1 involves serious computational effort. Probably in general it is impossible to avoid this, but we can use some freedom to choose a dynamical system y is equal to f of y. Now, let us here we get f of y is equal to y. Usually f of y is equal to minus grade of f of r, where z bar is a only global minimum for f, and roughly speaking f is equal to infinity on obstacle set. For instance, if there are no obstacles, then practically the same job will be done by the following the same job will be done by following dynamical system. Let us what is the system, let us know. Y is equal to k of y, f of y is equal to minus k of y grade of f of z, where k of y is equal to k transpose of y, into k of y, comma k of, where k of y is equal to k transpose of y means it is symmetric matrix, where k of y should be greater than 0. So we can use k of y is equal to c of y, c transpose of y, where c of y is a Lie bracket completion. Then step 1 is reduced to delta 1 bar, delta 2 bar, and so on, delta n bar a of ij, where ij are the range of ij is 1 less than or equal to I less than or equal to j less than j less than or equal to m is equal to c transpose f. This is real gain in computation. Somehow one can imagine a situation then if using this method motion planning by feedback is much easier and faster than by as open loop strategy. Now let us discuss step 2. What is step 2? Solution we used for decomposition of skew symmetric matrix is skew of that is equal to S. Works for arbitrary algebra. If elements a bar of aj belongs to the some field, then minimal of k is equal to rank of s by 2. Below we show that sometimes m minus 1 is an optimal number. Next is probably m minus 1 is a minimal number for a dimensional analog of a. There another issue in step 2 is let us illustrate is for the rolling disk example. This example 5x y is equal to u1 cos 5 u2 and sin 5 u3. Here is equal, that is equal to 1 0 0 that u1 plus 0 cos 5 sin 5 u3 belongs to are equal to bi u1 plus b3 u3. Now suppose that nominal system is u1 is equal to alpha 1 root 2 by l beta 1 cos t by e and u2 is equal to alpha 2 plus under root 2 by t beta 2 sin t by 2. Next, probably m minus 1 is a minimal number for an dimensional analog of a. There is another issue in step 2. I think this is already discussed. This is repeated. Next, we have to solve the following system of nonlinear equation. We have to solve the system of nonlinear equations. First one is alpha 1 minus beta 1 of delta beta 1 into beta 2 is equal to minus 5. Alpha 2 plus beta 1 into delta beta 2 into beta 1 is equal to minus of x cos 5 plus y sin 5. Beta 1 into beta 2 is equal to, by solving this 2, beta 1 into beta 2 is equal to x sin 5 minus y cos 5. To satisfy u1 of 0, u of 0, u2 of 0 is equal to 0, one needs beta 1, beta 2 is equal to 0. To satisfy u1 and u2 of 0 is equal to 0, we have to needs beta 1 and beta 2 should be 0. But there are no such differentiable solutions for beta 1 beta 2. So for the equation beta 1 beta 2, for equation beta 1 beta 2 is equal to x sin 5 minus y cos 5, we don't have beta 1 beta 2 is equal to 0 solution, in which so since beta 1 beta 2 of transpose y is equal to 0, not equal to minus 1, that is equal to x sin 5 minus y cos 5 by delta y. To fix this situation, we have to consider the following absolutely stable, not exponentially nominal system. Z is equal to mod z square z. If maximum order of Lie brackets in matrix C is k, then one has to consider nominal system. Z is equal to minus mod z of 2 power k z. This is about the topic. This is how we control the non-holonomic systems and decomposition of skew symmetric matrix. Thank you.